Okay, so given two propositions, sorry, I screwed this up a little bit here. Given two propositions P and Q, the statement P or true, the statement P or Q is called their, this is disjunction. And the disjunction is true unless P and Q are both false. So let me kind of outline a truth table here. So we got P, we got the statement Q, and we got P or Q. Okay, so let's go with P and Q are both true, P is true or Q is false, P is false or Q is true, and then they're both false. Let's look at the 4 different cases of that. Okay, so is P or Q a true statement? Well, if P and Q are both true, then one of them's true, so we're good, we're fine. If P is true, Q is false, P itself being true, so P or Q, that's actually true because P is true. If Q, so the third statement, P is false, Q is true, then the Q statement makes that true. And the only time where P or Q itself would be false is if they're both false. Okay, so how does this work in actual sentences? Consider the statement, airplanes can fly or cows can read. Is that a true statement? Well, let's define P to be the first statement, that airplanes can fly. And Q, we'll say, is cows can read. Okay, so is it true that airplanes can fly or cows can read? Well, let's start with airplanes can fly. That's obviously true. Airplanes definitely are flying. Can cows read? Not that I've seen. What about P or Q? So the fact that P was true, even though Q was clearly not true, means that I can claim that P or Q is true. So I can actually get away with saying it is true that airplanes can fly or cows can read. Whether we like to admit that or not, that is a true statement because of the word or and the fact that one of them is true. Okay, a statement of the form if P then Q is called a conditional proposition. Conditional proposition. Okay, or implication. It is true unless P is true and Q is false. So proposition is true unless one of those. Okay, so let me set up the truth table here. So we got P, we got Q, and then we have if P, then Q. Okay, so P itself could be true, Q is true, could be true, false, false, true, or both false. So let's talk about sort of the conditions on this. If P is true, then Q is true. That's a safe implication. If P itself can be true, Q can be false. But is if P then Q true? Well, because P is true, we're fine. We're starting off with the idea that P is a true. I'm sorry, that's not true at all. Let me go back. If P is true but Q is false, then there's no way that P implies Q because that's a false statement. If P is false but Q is true, can we say that Q is true? Well, yeah, in which case that's actually true because Q has nothing to do with is not connected with P in that sense. Q is already true whether or not F is true. P is true, sorry. And then Q, P. So if P is false and Q is false, can we say that if P then Q? Well, that's actually a true statement again. And the reason being, knowing that F was false, I also know that Q is false. So they're sort of linked together. Now, you might have encountered P's and Q's as something else. Typically in a science class, they call these hypothesis and conclusion. So the P statement, we call a hypothesis, and the Q statement we call a conclusion. Okay, and then there's several ways that we can rewrite this that mean the same as if P then Q. I'm not talking different forms of the statement, we'll get into that, but there's just different verbiage that we can use with this. So we can say P is sufficient for Q, and that means the exact same thing as if P then Q. P will lead to Q. P implies Q. So what we're doing is we're just making a list of all these things that sufficient will lead to, implies. We can even reverse the order. So we can say Q is necessary for P. We can also say Q if P, and we can say Q whenever P. All of these are just different words that mean if P then Q. Okay, now this is something else one might have encountered years ago in high school geometry, but this is typically when we talk about PQ statements, this is usually what we're thinking of as the conditional, converse, inverse, and contrapositive. So conditional would be if P then Q. Converse would be if Q then P. Inverse would be if not P then not Q. And your contrapositive is if not Q then not P. So we can illustrate this with just a very simple sentence. Let's just go, if it's raining, I use an umbrella. So if it rains, then I use an umbrella. Okay, so that's the conditional statement. What sentence would be the converse? So I'm going to switch the P and Q around, and it would be if I use an umbrella, then it rains. Okay, now we're not saying that's true or not, we're just saying that's the converse of the original conditional. The inverse would be if it does not rain, then I do not use an umbrella. And again, we're not saying that's true or false, we're just saying that's what the form of the sentence is. And then the contrapositive would be if I do not use an umbrella, then it does not rain. logically equivalent if they share the same truth values. So two statements are considered to be the same if they have the same truth tables. All right, so let's do a little chart here, and then we'll kind of hopefully outline this. So we got P, big old chart. So we got P, Q, not P, not Q. Then we're going to go the four different statements. So if P, then Q, if Q, then P, if not P, then not Q, and if not Q, not P. Okay, so let me outline the different possibilities here. So we have true, 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 false, false, true, and false, false. Okay, so we can fill some of this in pretty quick. So not P would be false, false, true, true. Not Q would be false, true, false, true. All right, and then we can just jump in here and start looking at if P then Q, which actually matches what we did earlier. So in other words, is Q true based on information P gives us? So if P is true, then Q is true. That's a true statement. If let's see, P is true and Q is false, then the FP then Q would be false. If P is false and Q is true, well, Q is already true. It doesn't really matter what P said. Q is true to begin with. And if P is false and Q is false, in other words, the two falses, does the false P give me information about a false Q? That's actually a true statement. That P does give me information about Q there. So let's switch the order around. What about looking at Q? So if Q is true, does that give me information about P? And that's true. So now we're saying P is the second statement. If Q is false, then P is true. Well, P is true no matter what Q tells me in that sense. Then the reverse. So if Q is true, P is false, that's actually false. And if Q is false, then P is false, that's true. So notice the last two rows, right there in the middle, you got F's that sort of switch places in the middle. So that's sort of a neat observation to make. Okay, inverse. So if not P, then not Q. So now we're looking at the nots column. So we got an F and an F, which is true. Here we got an F and a T, which is true. Here we have a T and an F, that's false, and a T and a T, which is true. And then the last column, if not Q, then not P. So not Q, so if false, false, that's true. True, false, that's false. False, true is true. And true, true is true. Okay. Now, why does this matter? Well, what do we notice about two sets of them? If you notice, the initial conditional statement and the contrapositive both share the same truth values. So we say then that the conditional and the contrapositive are logically equivalent. Same thing with the converse and the inverse. The middle two also share the same truth values, so they are defined to be logically equivalent to each other.